We have spent decades chasing machines that could outthink the universe itself, only to watch every promise dissolve into fragile noise. Qubits flickered for microseconds before collapsing, errors cascading like avalanches, turning billion-dollar labs into demonstrations of how unforgiving physics can be. Supercomputers laughed from the sidelines, their trillions of operations per second mocking the dream. But something has changed in the last 18 months. In quiet facilities across continents, researchers have watched error rates plummet. Not slowly, not incrementally, but exponentially, as the very act of adding more qubits began to make the system more stable instead of less. The math that once doomed quantum computing has flipped. Scientists now believe these machines are about to cross a major line, the one that separates noisy experiments from reliable engines of reality itself. To grasp why this line matters, consider what classical computers have always been fighting. Every bit flip, every calculation, demands precision in a world that refuses to cooperate. Thermal noise, cosmic rays, manufacturing defects, each one a saboteur that classical chips overpower with brute voltage and heroic cooling. The cost is thermodynamic: heat, energy, and an unbreakable speed limit imposed by the need to erase uncertainty. Quantum systems were supposed to bypass that wall by embracing uncertainty, letting qubits exist in superpositions that explore countless paths at once. Yet for years the opposite happened. The environment inside any real machine, vibrations, stray fields, even the act of measuring, destroyed those delicate states almost instantly. Decoherence turned promise into punchline. The gap between theory and hardware seemed unbridgeable. That assumption died when one advanced superconducting processor demonstrated something physicists had only modeled on paper. Researchers built increasingly large arrays of physical qubits and wrapped them in a surface code, an error-correcting lattice that detects and repairs mistakes without destroying the quantum information. With each step up in code distance, from 5 to 7, the logical error rate dropped by a factor greater than 2. The system crossed below the critical threshold. Adding more qubits no longer amplified chaos, it suppressed it. A logical qubit built from dozens of physical ones now outlived its best individual component by more than double. Real-time decoding kept pace at microsecond latencies across millions of cycles. The machine was no longer dying faster than it could think. It was learning to heal. This breakthrough did not arrive in isolation. Parallel advances in trapped ion architectures pushed fidelity to 99.99% for 2-qubit gates, the precision threshold, long considered mandatory for fault tolerance. Neutral atom arrays achieved magic state distillation at logical levels, feeding purified states into larger circuits without the overhead that once made scaling impossible. Photonic and hybrid systems began hinting at room temperature stability for communication links, eroding the cryogenic monopoly. Each platform attacked the same enemy from a different angle, yet all converged on the same revelation. The exponential suppression of errors is no longer theoretical. It is hardware reality in 2026. Scale that reality outward, and the classical wall shatters. Today's fastest supercomputers can simulate a handful of interacting molecules for a few picoseconds before approximations collapse the result. The number of quantum states required grows exponentially with every added particle. Exactly the regime where classical brute force dies. A fault-tolerant quantum processor does not approximate. It embodies the Hamiltonian of the system. Qubits interact under the same rules the molecules obey. The simulation runs in its native language. One recent demonstration solved a molecular energy landscape in under 5 minutes. A calculation that would require a classical machine longer than the age of the universe, multiplied by 10 septillion. That is not faster computing. that is computing in a different universe. The implications cascade immediately into material science: catalysts that split water with sunlight, superconductors that operate at room temperature, battery chemistries that store twice the energy at half the weight. These are no longer distant dreams. They are problems whose energy landscapes quantum machines can now navigate directly. Fusion reactor designs that once demanded years of plasma modeling can be stress-tested in hours. Climate models that currently simplify cloud microphysics into crude averages can resolve individual droplet interactions across global scales. The precision gap that has kept us guessing about tomorrow's weather and next decade's energy closes dramatically. Medicine stands at the threshold of its own revolution. Protein folding, the origami of life, governs every disease from Alzheimer's to antibiotic resistance. Classical algorithms still wrestle with approximations that miss critical metastable states. A quantum simulator settles into the true lowest energy conformation because nature itself seeks that minimum. Researchers can now watch a candidate drug molecule dock with its target in full quantum detail, predict off-target effects before a single animal trial, and iterate thousands of variants in an afternoon. The decade-long, billion-dollar gauntlet of drug development becomes an engineering loop measured in weeks. Personalized medicine stops being a slogan and starts being a simulation you run on your patient's unique molecular signature. Optimization problems that define modern civilization surrender next. Global supply chains, airline routing, financial portfolio balancing, traffic flow in megacities, each one a landscape of interdependent variables exploding into combinatorial hell. Classical heuristics guess. Quantum processors evaluate interference across all possibilities simultaneously. Early hybrid demonstrations have already slashed scheduling times from 30 minutes to under 5 in heavy industry. When fully fault-tolerant systems arrive, the savings will not be measured in minutes, but in trillions of dollars and millions of tons of carbon. Logistics becomes predictive rather than reactive. Scarcity itself comes under algorithmic siege. Even artificial intelligence transforms when quantum coprocessors join the conversation. Training models today devours energy because gradient descent crawls across lost landscapes one painful step at a time. Quantum kernels can sample high-dimensional probability distributions in a single coherent operation, accelerating feature selection and reducing the data hunger that currently starves frontier systems. Generative quantum AI begins to emerge, not copying patterns in training data, but exploring the latent space of physical possibility. The boundary between learning and discovering blurs. Yet the deepest shift is philosophical. Classical computers force the universe into binary decisions. Quantum machines ride its native probabilities. They do not calculate what nature might do. They become a mirror in which nature sees itself compute. Richard Feynman's old insight that simulating quantum systems classically is exponentially expensive has finally been answered by hardware that speaks the same dialect. The simulation no longer fights the territory. The map and the ground are the same substrate. Of course, crossing this line does not erase every obstacle. Qubits still demand exquisite isolation. Cryogenic infrastructure remains costly. Scaling to thousands of logical qubits will require modular architectures, photonic interconnects, and error-decoding chips that operate at quantum speeds. But the exponential curve has bent in our favor. Where once each added qubit multiplied risk, it now multiplies reliability. The engineering race has moved from survival to acceleration. Security experts are already mapping the aftershocks. Current encryption rests on problems quantum machines will eventually solve in polynomial time. The transition to post-quantum cryptography is no longer precautionary. It is urgent preparation for machines that will treat factoring large numbers as trivial arithmetic. Yet the same capability that threatens old secrets can protect new ones through quantum key distribution networks that detect any eavesdropper through the laws of physics themselves. The line we cross redraws both vulnerability and defense. Hybrid systems will dominate the near term. Classical processors handle the stable, predictable scaffolding, data movement, user interfaces, long-term storage. Quantum coprocessors dive into the probabilistic depths where classical logic drowns. The marriage is not compromise but complementarity. Your laptop will offload the impossible calculations to a cloud quantum module the way graphics cards once took over rendering. The average user will never notice the handoff, only the sudden disappearance of previously intractable problems. Look further, and the timeline sharpens. By the end of this decade, fault-tolerant modules capable of millions of reliable operations will exist in multiple architectures. By the early 2030s, systems running billions of gates on thousands of logical qubits will unlock simulations once reserved for science fiction. Entire chemical factories, atmospheric carbon capture pathways, even early models of quantum gravity. The machines will not merely answer questions we already know how to ask. They will reveal questions we never thought to pose because our classical minds could not frame them. This is the emotional core of the crossing. For the first time in history, humanity is building a computational substrate that matches the physical laws governing the cosmos rather than fighting them. The brain runs on 20 watts of wet chemistry and somehow produces consciousness. Photosynthesis harnesses quantum coherence at room temperature to move energy with near-perfect efficiency. Nature has always computed this way. We are finally learning the same language. The line is not a distant horizon. It is the edge we stand on right now. Every new logical qubit, every demonstration of below-threshold suppression, every verified advantage in a useful domain pushes us further across. The age of approximate computing ends. The age of embodied quantum reality begins. What secrets will these machines whisper when they achieve stable, long-running thought? Will they hand us room-temperature superconductors that make energy abundant and transport instantaneous? Will they map the exact folding pathways that let us cure diseases once considered inevitable? Or will they reveal deeper truths about the universe's own computation, about whether consciousness itself can be encoded in coherent states, about our place in a cosmos that may be running its own quantum program? The answers are no longer theoretical. They are being calculated in real time inside machines that have crossed the major line. The future is not coming. It is computing itself into existence right now. If this glimpse into the quantum frontier ignited even a fraction of the awe you feel when staring at the stars, do one thing. Share this with someone who still believes the impossible is merely undiscovered. Drop a comment with the single problem you most want these machines to solve first: cancer, climate, fusion, consciousness. And subscribe, because every new breakthrough will arrive here first, explained with the same relentless wonder that physics itself demands. The line has been crossed. The age of quantum reality is no longer a prediction. It is our present.